fact one, this pen. Fact is that this pen is not great. Let me grab, let me grab a new pen. Sorry, 1 second. Tell myself wanting a new pen. Fact. If two functions are inverses, then f of g of x equals g of f of x equals x. And another fact, if two functions are inverses, then they will be mirror images of each other. Across the line y equals x. So there's a couple examples. So let's look at the functions e to the x and the natural log of x. So let's do e to the x in red. So f of x is e to the x, which we know has a horizontal asymptote, intercepts at 0, 1. It looks like this. There's e to the x. And here is the natural log of x. Oh, can I go back real quick? Sure. So if two functions are inverses, f of g of x equals g of x equals x. And if two functions are inverses, then they will be mirror images across the line y equals x. The other function, g of x, natural log of x, looks like this. So x-intercept at 1, 0, has a vertical asymptote, and hopefully you guys will agree, and I would encourage you to look at this on Desmos if you have the time, that these are definitely mirrored images of each other across the line y equals x. In fact, right, you can plot, really the thing I'm thinking of is just the x and y values are interchanging, right? I get 1, 0 and 0, 1. Or I have the point on the red graph, if I plug in 1 for x, I get the point 1 comma e, which is about 1 comma 2.7. And if I plug in e for this one, I get e comma 1. So all the xy coordinates are inverses of each other. And another important fact, this is the fact that we're going to focus on today. That's the one up. The domain of f of x is equal to the range of f inverse of x. In this particular problem, the domain of f of x in red is everything, and the range of the inverse function is also everything. It's also true about the other part, meaning it's also true that the range of f of x is equal to the domain of the inverse function. This should make sense, because if you're switching x and y to find the inverse function, well, x is all the domain is all the x things, the range is all the y things. If you're switching x and y, you're switching the domain and the range. So let's look at another example. This example isn't going to be too particularly exciting as far as the domain and the range term go. But let's look at the functions f of x equal to 2x minus 4 over 3 and g of x equal to 3x plus 4 over 2. These are definitely inverse functions. You can either talk it out and say, oh yeah, f first multiplies by 2, then subtracts 4, then divides by 3, and g totally undoes it. The first multiplies back by 3, then adds back the 4, then divides by 2. We can also do the work. We can see that f of g of x is equal to f of 3x plus 4 over 2, which is equal to, so I'm putting this in for x here, so it's 2 times 3x plus 4 over 2 minus 4 over 3. We have to be a little bit careful about the order we cancel things in. Or, they were. First, we cancel these 2's. Then I'm rewriting this as 3x plus 4 minus 4 over 3. 4 minus 4 cancels out, that's 0. And then we got 3x over 3, those cancel, which is x. So f of g of x is x. And unfortunately, it is true that we have to check both directions. We do have to check that g of f of x is also equal to x. So I'm going to get g of 2x minus 4 over 3, which is going to be 3 times this plus 4 over 2. And then I can cancel things in the same sort of way. The 3's cancel there. You get 2x minus 4 plus 4 over 2. Minus 4 plus 4 cancels. You get 2x over 2. The 2's cancel. You get x. Okay, so we can show their inverse. So we can also graph them. So I'm going to graph both of these lines. This doesn't dry out. So I'm graphing f of x equal to 2x minus 4 over 3. And g of x equal to 3x plus 4 over 2. Let's graph g first. So to graph this line, and I know it's a line because I have x to the first, I'm going to find my intercepts. So a y-intercept is at x equal to 0. I'm going to get, let's see, if x is 0, I get 0 plus 4, which is 4. 4 divided by 2 is 2. So g of 0 is 2. So I get the point 0, 2, and I should be kind of extra careful here, make sure that things are fairly precise. 0, 2. And then if I find the x-intercept, I'm going to set y equal to 0. So I set y equal to 0. I'm solving this equal to 0. So 3x plus 4 over 2 equals 0. I can multiply both sides by 2. Get 3x plus 4 equal to 0. Subtract 4. Divide by 3. So x is negative 4/3. And let me see one thing here. Yeah, negative 4/3. So I just want to check one thing. Sure, all right. So yeah. Sorry, I feel like I'm making a mistake in my brain. Let me just sorry, let me okay, yeah, sure. Sorry, I was trying to plot a point that's not really there. Okay. So there's my line in red for g of x. And now, what's true is that f of x, we could, if we really wanted to, just say, well, it's going to be the reflection of this red line in the line y equals x. And they'll eventually cross each other. Now, what I'm really going to do is I'm just going to switch the x and y intercepts. So for the red function, my y-intercept is 0, 2. For the green function, my x-intercept is going to be 2, 0. If you plug in 2 for x, 2 times 2 is 4, 4 minus 4 is 0, 0 divided by 3 is 0. You get 0 for y. In a similar way, the x-intercept here was negative 4/3. the y-intercept here is going to be -4/3. If x is 0, 0 minus 4 divided by 3 is -4/3. So you exactly get this interchanging of all points, right? This is the point 0, this is the point 0, -4/3. And eventually they would cross each other, and they will cross each other right on the line y equals x. Right there, that. And hopefully you believe my picture, right? This red thing is a reflection of this green thing across the line y equals x, which really, really, really shows the nature of interchanging the x's and the y's to get the inverse function. Okay, let me grab this. So the point of this, or one of the points, this is not the only point, but one of the points of this is that you can use the inverse function to find the range of the original function, especially when the range or the function is hard to graph, or even when it's not. Now I will say this only works if the function is invertible, or it has an inverse. So let's find the domain and range of f of x equal to x plus 3 over 3x minus 5. And I will say, we probably could graph this one and figure out what the domain and range were graphically, but we're not going to. So for the domain, usual stuff, we're going to see, well, we know we can't divide by 0. So we're going to exclude where the denominator is equal to 0. We know we also can't take the square root of a negative, and we also can't have a logarithm of a negative or 0, but neither of those are issues for this particular problem. So we're not going to worry about them. Okay, so I'm trying to make, yeah, okay, good. So let's see, 3x minus 5 equals 0, 3x equals 5, x equals 5/3. So that's the only thing not in the domain. And we want to exclude that. So we want everything from -infinity to 5/3, union 5/3 to infinity. That's our domain. To find the range, we have to find the inverse function. So to find the inverse, we switch x and y. I suppose we call this y, and then we switch x and y. So we're going to have, instead of y equal to x plus 3 over 3x minus 5, we're going to have x equal to y plus 3 over 3y minus 5. So we switched x and y. Now we're going to solve for y. We're going to multiply both sides by this denominator. So we're going to have x times 3y minus 5 equal to y plus 3. Distribute the x. 3xy minus 5x equals y plus 3. Bring all the y's on one side together and all the other things on the other side together, meaning put all the y's on the, I don't care which side, left, and all the not y's on the right. So subtract y, so 3xy minus y, and add 5x equals 5x plus 3. Factor out the y, that's why we brought them all to the same side, pun intended. Y times 3x minus 1, right, dividing out the y, equals 5x plus 3. Divide by this, so y equals 5x plus 3 over 3x minus 1. And that's our inverse function. So the inverse function, f inverse of x, is equal to 5x plus 3 over 3x minus 1. We can use the domain of this to find the range of that. So the domain of f inverse, well, we want to, again, exclude where the denominator is 0, which in this case is where 3x plus minus 1 equals 0. So we want to exclude 3x minus 1 equal to 0, or 3x equal to 1, or x equal to 1/3. So the range here, the domain of f inverse, which is the range of f, is everything except for 1/3. So the domain of f inverse of x is the range of f of x, and it is everything except for 1/3. So negative infinity to 1/3 union 1/3 to infinity. I will point out that for this particular example, you can see that 1/3 also isn't in the range because this function has 1/3 as a horizontal asymptote. And this definitely would have a graph that didn't cross its horizontal asymptote. In a similar way, you can see that 5/3 isn't in the range of the inverse because 5/3 would be a horizontal asymptote. And 5/3 isn't in the domain of the original, so it's not the range of the inverse. Again, the theme of today is the theme of today is domain and range interchange when you find the inverse function. Let's look at another example. Find the domain and range of f of x equals to the log base 3 of x plus 3. Okay, domain, no big deal. You can say x plus 3 has to be greater than 0. So x is greater than 3. So our domain here is negative 3 exclusive to infinity. The range we could find in a number of ways. We could graph it. And this is your regular logarithmic graph shifted 3 to the left. So it would look like this. The vertical asymptote would now be at negative 3. It would look like this. What's the range of that function? Good question. What is the range of that function? Down to negative infinity up to... Does it ever stop?
No.
No. So the range is everything. So here you could just find the range graphically. You could also find the range by finding the inverse function. So you could start with y equal to log base 3 of x plus 3. You could interchange x and y. So 3 to the y equals 3 to the y equals x plus 3. Oh, I forgot to interchange x and y. Sorry, let me do that first. You don't have to do that first, but we usually do it first. X equals log base 3 of y plus 3. Then we write it as an exponential. 3 to the x equals y plus 3, and then y equals 3 to the x minus 3. So our inverse function, f inverse of x, is 3 to the x minus 3. And certainly the domain of this function is everything, right? There's no division by 0, there's no square roots, there's no logarithms. So the domain here of f inverse of x is everything. Negative infinity, which means that's the range of the original function. Okay. So let's look at some more examples. Not every function can be done this way because not every function is invertible. To be invertible, a function has to have pass the horizontal line test, meaning if you draw a horizontal line, it can only go through at most one point. Here's an example that doesn't follow that. So what about the domain and range of the following function, f of x equal to the square root of 9 minus x squared? Let's talk about domain first. Domain, we need 9 minus x squared to be greater than or equal to 0. I prefer to factor. Oh. How do you know the range? Sure. So for the previous example, when I'm looking at the inverse function, which is 3 to the x minus 3, I'm looking for the domain of that. When I'm looking for domain, I'm really looking for the 3 problems. Division by 0, no division here, so no division by 0. Logarithms, there's no logarithms there. Or square roots, there's no square roots there. So since I don't have any three of the problem functions that make it so the domain is limited or restricted, I know the domain is everything. So typically our base assumption is the domain is going to be all real numbers unless you have division by zero, square root of something that could be negative, or the logarithm of something that could be negative or zero. So that's how we know. Just like in this one, finding the domain, we have to consider where the insides might be negative. So we want the insides to be non-negative. I'm going to factor. This factors is 3 minus x times 3 plus x. I'm going to use the number line. I'm going to plug in x equal to 3, because that makes this 0 and negative 3. And I'm going to test the point in each region. If x is bigger than 3, like 4. Negative times a positive is negative. X is 0, positive, positive. X is negative 4, positive, negative. I want it to be greater than or equal to 0, so I want it to be positive or 0. So my domain here is negative 3 to 3. Anything between negative 3 and 3 is fine, right? If you plug in 3, 9 minus 9 is 0, square root of 0 is fine. If you plug in negative 2, 9 minus 4 is 5, square root of 5 is fine. But if you plug in something like 5, 9 minus 5 squared is 9 minus 25, which is negative 16, and the square root of negative 16 is imaginary. Now, the problem here is that the range is not so easy to find. And we can't just find the inverse function here because it just doesn't really work. I mean, it doesn't work. Sure. I'll talk about it in a minute. Right, so let's pretend that we did try to find the range the way we'd be doing. If we switch x and y, so we say, like this is x equal to the square root of 9 minus y squared. If we solve for y, we get x squared equal to 9 minus y squared. We get x squared plus y squared equal to 9. We get y squared equal to 9 minus x squared. We get y equal to the square root. We actually get back the function we started with. We do include the 3 because if you plug in 3, 9 minus 3 squared is 9 minus 9, and 9 minus 9 is 0, and the square root of 0 is a real number. The square root of 0 is 0. So for square roots, you always include the points that make the insides equal to 0. So we do include the 3 and the negative 3 here. So here's the thing. If this was my inverse function, which is not really, then the domain and the range would be the same, right? Because if it's the same function, the range should be the same as domain. However, if you graph this, well, the thing is, this is a circle. And if you graph the whole circle, you're right. The domain and the range would be the same. Let me go to the other side here. Okay, if you graph the whole entire circle, center of 0, 0, radius of 3, totally would have the same domain and range. Problem is, this function is not a whole circle. Well, one, it's a function, right? If it's a function, and it is a function, it should pass the vertical line test. It doesn't pass the vertical line test. So what's happening here? Well, the problem is, when you take a square root of something, square roots only give you positive or 0 results, right? You can't take the square root of a number and get a negative answer. Square root of 0 is 0, square root of 4 is 2. It's not plus or minus 2, it's just 2. Square root of 9 is 3, not plus or minus 3, just 3. So the problem here is that this function, the y values can only be positive. So really, we're getting just the top half of this. This is your f of x equal to the square root of 9 minus x squared. And this other thing here, this is the equation, or the graph of the equation, x squared plus y squared equal to 9. And the difference between this and this is that here it's okay for y to be negative, right? If x is 0, y could be 3, or y could be negative 3. Here, if x is 0, y is only 3, because the square root of 9 is only 3, not plus or minus 3. However, that doesn't allow us to answer. If we know the graph, which we do know the graph, we know it's the top of a circle of radius 3, we can find the range by saying, okay, well, graphically, the range goes as low as 0, inclusive, so we use a bracket, and as high as 3, inclusive, right? We get that y value of 3, so we include. Yeah, let's look at this next one. This next one's a little bit trickier. So this next one is the following. Find the domain and range of f of x equal to 20 over x squared plus 4 when x is greater than or equal to 0. Now, there's something going on here. And so we're going to find domain and range, but that's kind of a dumb thing to say. Well, not dumb. It's kind of silly to ask about the domain when they've already made the domain explicit. So here the domain is just x is greater than or equal to 0, which is just everything from 0 inclusive to infinity. Now, why are we doing this? Why are we explicitly stating what the domain is? Well, it's because if you look at the graph of this function, 20 over x squared plus 4, it does this. It's got a horizontal asymptote of 0, right? The degree on top is 0, the degree on the bottom is 2. Since the degree on top is less, it's got a horizontal asymptote of y equals 0. And it looks like this. If x is 0, you get 5. That's kind of this deal. And the problem is, this function doesn't pass the horizontal line test. It's not one-to-one, so it's not invertible. Right? If you interchange x and y, if you flip this graph across the line y equals x, it looks like this. So this is, let me write this here. This in black is y equal to 20 over x squared plus 4. And in red, I'm going to switch x and y. So here is the inverse relationship. And the problem is, I think you guys can all see this function in red fails the vertical line test. So it's not really a function. I should say this graph in red. But this is definitely the equation, x equal to 20 over y squared plus 4. So here's what we do to fix it. We say, well, I don't want all of this black graph. And I want the half when x is positive. Well, that's going to correspond for the red graph only having the half when y is positive. And now it's more clear that this function, this thing in red, this inverse function is a function. So in fact, you can even use this graph, if we're smart, to say, oh, well, it looks like the domain is 0 to 5, which means the range of this is 0 to 5. But let's pretend like we didn't know what the graphs were. So let's use the inverse to find the range. So first we're going to switch x and y. So x equals 20 over y squared plus 4. Now I want to be very, very specific here. I'm trying to find the range, because I'm trying to find the domain of f inverse of x. I want to ask you guys all a question. If the domain of this is 0 to infinity, the domain of f is same as the range of what? Well, I know it's kind of hard to type it. I'll just say it. It's the same as the range of f inverse. So since I know the domain of f is 0 to infinity, I know the range of f inverse is also the square root of infinity. I'm trying to find the domain of f inverse to find the range of f of x. I know we're getting kind of complicated here, but that's what we're trying to do. Okay, so I'm going to solve for y. I'm going to multiply both sides by this. So we get y squared plus 4 times x equal to 20. And now I am going to, how do I want to do this? Yeah, I'm going to divide both sides by x. So I'm going to get y squared plus 4 equals 20 over x. Then I'm going to subtract 4. So y squared equals 20 over x minus 4. And finally, I'm going to take the square root of both sides. Now, technically, when I square root both sides, I should get y equal to plus or minus the square root of 20 over x minus 4. However, I know that y has to be positive. Why? Well, because the domain of the original function was positive. So the range of the inverse function should also be positive. So there's my inverse function, 20 over x minus 4. Or if you prefer, yeah, sure. I can write this as f inverse of x is the square root of, I can multiply this by x over x and say it's 20 minus 4x all over x. Okay, so my job now is to find the domain of this. So first off, I see that x can't be 0, because that'd be bad by 0. Second, I need the insides to be greater than or equal to 0. Now here's something we can't do. We can't multiply both sides by x. Why not? Well, I guess we could. We just have to be extra super careful, and there's an easy way to deal with it. The reason we can't multiply both sides by x is because I don't know if x is positive or negative. Because I multiplied this by x over x to get a common denominator. That's why I got a 4x there instead of just a 4. But what I was saying, the reason we can't multiply both sides by x is because if x is positive, okay, it's fine. But if x is negative, then when you multiply both sides by a negative, you have to change the order of the inequality. And I don't have to deal with one inequality when it's positive, one inequality when it's negative. I would rather just leave this as is and say, okay, well, I'm going to look at the places where this is either equal, where it can change signs. And it can change signs when it's either equal to 0 or when it's undefined. It's equal to 0 when x is 0. It's undefined when x is 0, right? If x is 0, this whole thing's undefined. And because we're taking a square root. And so the reason we set it to be greater than or equal to 0 is because we can only take the square roots of numbers that are greater than or equal to 0. And we can't take the square root of a negative number. It's not real. So 0 makes this undefined. And if x is 5, 4 times 5 is 20. 20 minus 20 is 0. So the places where this can change signs are at 0 and at 5. If x is bigger than 5, like 6, 20 minus 4 times 6 is 20 minus 24, which is negative. The bottom is positive, and a negative divided by positive is negative. And that would be true for any number larger than 5. And if I pick 7, 20 minus 4 times 7 is still negative, the bottom is still positive. If I pick 10, 20 minus 4 times 10 is still negative, the bottom is still positive. If I pick something between 0 and 5, like 1, 20 minus 4 times 1, that's positive. The bottom is positive. Overall, it's positive. And again, that would be true for any number we pick between 0 and 5. We could pick 4. 20 minus 4 times 4 is 20 minus 16, still positive. Bottom, still positive. And then we can pick a number over here like negative 1. 20 minus 4 times a negative number will always be positive. I got the 5 by seeing where the top was equal to 0. So again, when I'm trying to find where something might be positive or negative, I really want to know where it's either 0 or undefined. So pick a number like -1, the top is definitely positive. I also could say I could have factored out 4 from the top. I could have written the top as 4 times 5 minus x all over x, and then it's a little bit more clear that 5 is a number that makes it all 0. But if you pick a number less than 0, like -1 or -2 or -3, this is going to be positive because 5 minus a negative number gets more positive. And the bottom is going to be negative. I want the whole thing to be greater than or equal to 0. So I want it to be positive or 0. Right? When I plug in 5, it's 0, but not undefined. Right? We already said x can't be 0. So my domain here is 0 to 5, which is the range of this. This can be almost as small as 0, right? You can get really, really, really small. In fact, we can go back to the graph if you guys want. If you remember, the graph of that thing looked like this. Had a y-intercept of 5. When x is 0, 20 over 4 is 5. And then when the x values get bigger, the y values get smaller. But they never get as small as 0, right? This can never equal 0, but you can get really, really, really close to 0. So that's the range. It's probably easier to see the range of this one graphically, but it's worth noting, especially if you're going to take the 17 series, there are definitely questions like this, where they give you a function with a restricted domain, and they ask you what the range is, and they want you to kind of do it this way. Right, so the range of the original problem is 0 to 5. So I should say the range of f of x equal to 20 over x squared plus 4 is equal to the domain of f inverse of x, which is this thing we found here, the square root of 20 minus 4x all over x, and it's equal to what we found, everything from 0 exclusive to 5 inclusive. Yeah. So the range of the original, it's the domain of the inverse. Cool. Yeah, that's it. Is that all I have? I thought I had more. Let me look and see. That's all I have. I could say more. Let me show you guys another one, just because we have time. This is literally from a 17A class that I was working on earlier today. So let's say that f of x is equal to 2x squared plus 8 for x greater than or equal to 0. And so we have a vague idea of what this looks like. It looks like your usual parabola shifted up by 8, maybe stretched vertically by 2. It looks kind of like this. Right, if x is 0, 0 plus 8 is 8. If x is 1, 2 plus 8 is 10. And so on and so on. And so we could probably figure this one out graphically if we wanted to. We'd say, well, I'm going to switch the x's and y's. So instead of getting 0, 8, I'm going to get 8, 0. And instead of getting 1, 10, I'm going to get 10, 1. And so it's probably going to look something like this. You know, I didn't draw it very nicely, but right? There's supposed to be a line of symmetry. Okay. It's not the best. But the point is that if I had to guess, I would guess that we can also see the range just by graphing this, right? You can totally see the range here is just 8 to infinity. But I could also find it by looking at the inverse function. Say, okay, well, if I find the inverse function, I'm starting with y equal to 2x squared plus 8. I'm switching x and y. Solving for y. So first I am subtracting, maybe, I don't know, yeah, sure, subtracting 8. So x minus 8 equals 2y squared. And then dividing both sides by 2. Or multiply both sides by 1/2. So that 1/2 times x minus 8 is equal to y squared. And then finally, now this is where you have to be a little extra careful. Y is equal to plus or minus the square root of 1/2 times x minus 8. However, we know that since the domain of f of x is x greater than or equal to 0, the range of the inverse has to be that y is greater than or equal to 0, which means it has to be the positive, not the negative. So then you can see, oh yeah, look, the domain of this, well, I need the insides to be greater than or equal to 0. So 1/2 times x minus 8 has to be greater than or equal to 0. Multiply both sides by 2. Sorry, I'm running out of room here. You get that x minus 8 is greater than or equal to 2 times 0, which is still 0. And then add 8 to both sides. Oh yeah, x is greater than or equal to 8. So we can see that f inverse of x, which is equal to this function, the square root of 1/2 times x minus 8, has a domain of 8 inclusive to infinity, which means that the original function has a range of 8 inclusive to infinity. Oh, sorry about that. Oh. Right, that's all I really have to say.